So we've got a car depreciating. So if the growth rate is 82%, what's it depreciating by? How much is it losing each month, each year, sorry? What's that? 82% is what the value it retains. It would be 18% that it's losing. Yeah, so this is a depreciation rate of 18%. Take 18 from 100, that leaves you 82% to keep. Okay, so that's where the formula came from. The initial value of the car is $18,000. We want to figure out when it's going to be worth $12,000. So starting with the equation, the value over time is going to be the initial value times that repeated multiplication by 82% value of the car we get to retain. Question for us is, when is the value equal to 12,000? So we just need to set our equation equal to that and solve. So I'm going to take my 18,000 times 0.82, raise that to the power of t, set it equal to 12,000. What do I need to do first to solve this? I'm going to break that multiplication. We're going to divide by that 18,000. And so that's going to give me 82% to the power of t. Let's see, cleaning that up, we can divide by 1,000 pretty easily. Then we get 12 over 18. And I'm not too worried about simplifying that more. We could divide top and bottom by 6 and get it to 2/3, which is fine. The bigger picture is, what do I do next to get the exponent out? There's two options. What's that? No. Log, yeah. To get the exponent out, we need a logarithm. Okay. So t is the exponent. It's going to be equal to what? The log. Okay. And what is that, Emily? The log of what? That's going to be the base of the logarithm. So I'm going to write that down here. And then the target of the log is whatever's on the other side. So in this case, it would be the 12/18. Or if you chose to write this 2/3, that goes on the other side. So key points to this conversion right here is the base of the exponent has to match the base of log. Now the calculator doesn't have a 0.82 button, so we need to rewrite it with our trick. So the rewrite here is going to be log base 10 of 12/18. And how do I adjust that? To deal with the base I want. What's that? Divide by what? The log of the base that I should have had. Yeah, the 0.82. All right, so that should give the answer right there. So plug that into the calculator, see what you get. Everybody give that a shot. I'm going to do it on a spreadsheet. I haven't used spreadsheets and logs yet. So let's go to my drive, math class, Quantlet. Let's make a new sheet for this. So here, I want to type a formula. If I start typing LO, it gives me a bunch of different options. It says log, which is the log of a number with respect to a base. So that's interesting. What does that mean? If I hit enter, it'll tell me more about it. And it says, give me the value I'm trying to find the log of and the base. So this is kind of cool. It does the base thing. So I would tell it 12/18, comma, and the base was the 0.82. And I get about 2 years. Is that what you guys got? You plugged it in? Okay, so spreadsheet gives us a slightly different way to enter it, which is kind of nice. A log of any base. So I'm going to do this one more time to check the answer using the method the worksheet goes over. So let's go back to the point where we're at log, no, before the log, sorry. We've got 0.82 to the power t equals 12/18. And I'm not going to change that to a decimal, 12/18, because then I have to round it, and I don't have to worry about that. Does anybody remember the technique the book shows, or the worksheet shows for this? It's on the second page, maybe the third page. The book says, like you can square both sides or add 2 to both sides, you can take a log of both sides. So the book says take the log of the left side, so you'll have the log of 0.82 to the power t. On the other side, you'll also take the same log of 12/18. Now, in this worksheet, before this problem, we went over a special property of logs and powers. What's that property? What happens to the power here? The property is the power comes out as a multiple. So this left side, I can pull that power out, so it becomes t times log of 0.82. On the other side, I still have the log of 12/18. Pen's malfunctioning. I think it's the pen. So t is now what I'm trying to solve for, right? How do I break multiplication? Division, so I divide both sides by this log of 0.82. And that gives me the answer I found the other way. So you need to decide which method you like, the method the worksheet goes over or the method I go over for translating. It's about the same amount of steps, it's just a slightly different perspective on the problem. But you get the same exact answer either way. That's that same 2.04 we found earlier. Okay. If this looks foreign, that means you skipped that part of the worksheet. I highly recommend you look back at it because it can be a useful way to look at it. All right, so we found that the car will depreciate to about $12,000 in about 2 years. So don't forget to put your answer in context after you calculate it. All right, we're going to try a similar one from the homework. Which one was it? Number, what's that? No, we need to, Emily, come on. What fun would it be if we didn't? Number 8, I think, is just like that. Yep, I'm going to copy that into my notebook. All right, so you guys give this a shot, and then we'll check answers in a minute. So pretty similar. We still have that same losing 18%, which means we keep 82%. But this time the vehicle is starting off at $8,000, and we want to know when it's going to drop down to $3,000. So see if you can calculate that to the nearest tenth of a year. I need a calculator for this and to write something down. you think they have? Number of years? What do you think, Jenna? 5 years? Seems reasonable. Anybody else get 5 yet? I think get about 5 years. What are you guys doing? Not sure. Emily? Not sure yet? Okay. So here's the way I would work it out. Starting with the formula, 8,000 times 0.82 to the power t. I want to know when that is going to be equal to 3,000. So that's the first step, getting that started. Once I write that down, what should I do next? Yeah, divide by the 8,000. So that's going to leave the 0.82 to the t alone, and that's going to give 3,000 over 8,000 on the other side. Now that cleans up just a little bit, right? I can divide by 1,000 and get 3/8. Okay, so then we have choices to make. Should we use the method where we just rewrite it as a log, or we take the log of both sides like the worksheet? Suggestion? Log of both sides? Okay. So if I take the log of both sides, I'll get the log of 0.82 to the power t. Oops, that t in there. Equals the log of 3/8. All right, what's the next step then? We take this approach. What's that?
As far as I go.
Okay, so anybody else want to suggest what to do next? With this approach? Not sure. So with this approach here, the rule is that if what you're taking the log of as an exponent, that exponent pops out front. So this will become t times the log of 0.82. Okay, so that's the rule we're applying. The rule is exponent comes out as a multiple. On the other side, it's still unchanged. It's still just a log of 3/8. And so now I'm at a place where I can divide by that log of 0.82. So I think t is whatever this comes out to be, log of 3/8 over the log of 0.82. And I had a couple claims that that's approximately 5, 4.9-ish. Yeah, that's close enough to 5. So just double check log of 3/8, close parentheses, then divide by the log of 0.82. No, 4.9-ish. So we'll call it about 5. So approximately 5 years. Now, just to show the other way again, I'm going to pick it up from the point where the log of 0.82 to the t equals the log. Oops, no, I have myself there. Step before that. Where we have 0.82 to the t equals 3/8. So the other way to look at this is to say, well, the exponent t is a log. And then I have to identify two parts. What's the base and what's the target of the logarithm? So what's the base of the previous line? Yes, that goes down here, 0.82. And then the target is the 3/8. And then we just use that rule to rewrite as the log, which is log base 10, divided by log base 10 of the old base. So that's the other way. It's about the same amount of work, it's just two different perspectives on it. Either way gives you the same answer every time.
Professor, I have a question.
That's easy.
I did natural log using for this question, and I got the same answer.
Yeah,
so I'm a little confused with natural log and log.
About logarithms, the base is kind of irrelevant in some circumstances. I'm not going to say it's completely irrelevant because it's not. But in this example, it is. So I preferred log base 0.82, but that doesn't exist on my calculator, so I switched to log base 10. It turns out log base 10 isn't special. There's another logarithm called the natural log, ln. And so see if your calculators have a button for the natural logarithm. It turns out it doesn't matter which log you use as long as it's the same one. So if your calculator doesn't have that ln button, then don't worry about it. So I could switch from log base 10 to the natural log. It's called ln, and I'm going to get exactly the same answer. So somebody might try to take that a step further to say, well, if the log is irrelevant, why not just get rid of it? So let's test that theory. What if we just ditched the log completely and tried to take 3/8 and divide by 0.82 and just bypass the logs completely? It ain't gonna work. The logs are important, even though it doesn't matter which log you pick, as long as you're consistent. So if on my calculator I say, okay, what is 3/8 divided by 0.82? My calculator says it's 0.45. And you might say, well, you didn't use parentheses right. You got to put that 3/8 in parentheses, okay? At the same number, which isn't the answer I want, okay? It's not a multiple of the answer I want. It's just totally wrong. So logs are important, but there are different options for the kind of log you can pick, okay? All right, good question, Daisy. Does that help at all?
Yeah, but I'm a little confused when you use it.
The natural log?
Yes.
You, if you're using the approach the workbook uses, where you take a logarithm of each side, it doesn't matter whether you use the natural log or the common log, which is the base 10. So you can pretty much arbitrarily switch between them. You just have to choose a logarithm. So let's do another problem. All right, so I'm going to switch back here to problem 7. So problem 7 has no context. It's just, hey, here's a problem with an exponent. Can you solve it? So I'm going to screenshot that and blow it up a little bit. What should x be here? Use either approach. Try something. Write something on paper and then whip out your calculator. So either of those should give me exactly the same answer. And on the spreadsheet, I can actually type this almost the way I see it. So let me switch back. On a spreadsheet, I could do log base 46 by using what they call LOG. Put the target in first and then the base in seconds. So this is on a spreadsheet. Target number, comma, base. So that's kind of a third way related to method one. So let's get a number on a calculator and see if you guys agree with me. Here's my spreadsheet. So using the spreadsheet formula, LOG 66 with a base of 46, I get 1.09. Anybody else get that number? Okay. That, we got 1.08. Type something wrong. Oops. Let's see. 66 over 46. Let me type it another way just to see. Other options are log base 10. And then I would have to do the 66 close divide by log base 10 of 46. I should get the same number, 1.09. You must have mistyped something there. So this one right here is like typing a base 66, or sorry, base 46 log. This one here was log base 10. And then do we have the natural log on a spreadsheet? ln, there it is. Oh no, that's, oh yeah, ln, that's it. So I could still do the same thing as long as I close my parentheses in the right spot. They're all going to give exactly the same number. So when you're solving an equation with logarithms, you pick any logarithm you like, depending on the calculating tool you have. So if your calculator doesn't have a natural log, don't use it. Some people I know like natural log because writing it on paper is one less letter. So take your pick.
Can you go back to when you were talking about method one and two?
Yes. Yeah. So method one is the method I typically use, and that's where I just rewrite the exponent as a logarithm. And the rule there is I write down the exponent first, and an exponent is a logarithm. The base of the exponent has to match the base of the logarithm, and then the other number is always the target value. And then from there, I can either rewrite it with log base 10. I could have rewritten this as natural logarithm also. We're going to talk more about the natural logarithm in section 4 today. All right, converting exponents to logs. We have two options. We're going to keep doing this for the next couple of lessons, so hopefully you'll get more used to it. And really, it's something you got to get used to. Are there any other questions about the worksheet or the homework? Not at the moment? Okay, check again tomorrow. So I've got another problem for you. Let's look it up on the home page. So it's going to take us a couple of days to get through the scale to fit lesson 4. I made some printouts for those of you here that don't have it. It's going to start off pretty similar to what we've already been doing. Somebody asked the other day about carbon dating items, and there's a formula here for carbon dating with what's called carbon 14 and how it changes over time to carbon 12. And if we look at it, if we measure how much carbon is in an object and we look at the ratio between carbon 12 and carbon 14, it gives us an estimate of how old it is. And the formula for it right here, A equals the 0.8861, that just tells us the fraction of carbon-14 that's remaining after, guess what T is here? 1,000 years. Yeah, that's a long time. Okay, so over 1,000 years, we lose like 11 or 12% of the carbon-14 that's in it. It shifts over to carbon-12. So what you're going to start off by doing is just making a table for this. Now, ultimately, I want you to make that table on a spreadsheet in addition to putting it on paper. So if you don't have a computer with you right now and you want to move over to the lab, that's fine. And then we're going to talk about the idea of half-life, and we're going to repeat that table using the idea of half-life. So I'm just going to go over half-life again. We'll apply it to this problem, then I'll set you guys free to work on it. So did anybody remember what example I used for half-life the other day? It was the ibuprofen, how it dissipates out of your body, how it's metabolized. So half-life applies to a lot of different things. And it's related to any situation where you have exponential decay. So examples of exponential decay are, like with the carbon example, that's an example of exponential decay with radioactivity. Where else have we seen exponential decay? Ibuprofen, right? So drugs getting metabolized or substances getting metabolized. Where else have we seen exponential decay? The model we're using with that equation for alcohol, we're actually using a linear model for that, but there are some people that use an exponential model instead, so that could apply, but just not the formula we've been using. But there is a different one that's an exponential decay. What two problems did we start off class with today? Depreciation. It's dropping, that's a decay. So depreciation of value. So that's exponential decay versus exponential growth. That's going the other direction. So like when you make a financial investment, compound interest, that's exponential growth. When we're talking about things dropping, there's going to be a point at which we have half of what we started with. Like an 18,000 cars are eventually going to be worth $9,000, right? When we go the other way, like growth of money, there we usually talk about doubling time. That's a popular thing to look at in finance. So they're both similar ideas. So they occur in these situations and many more, but half-life is just the time until some value is half of what it was. Okay, so whatever time goes by and it was half of what we started with, that's the idea of half-life. And the crazy thing about half-life is if you do have exponential decay, half-life is always the same for any particular situation. Like with straight lines, slope is constant. With anything that's exponentially dropping, half-life is constant. Okay, so it's a different kind of slope. So let's just go back to the ibuprofen example. In the ibuprofen example, we had time in hours, and we had the amount, I'll call it A, of ibuprofen. Let's spell it right today. And initially, I think the other day, we started off with 100 milligrams of ibuprofen. What did we go with for the half-life? It was, well, 50% is what we'll end up with, but how much time does it take? 2 hours, right? So 2 hours later, we ended up with 50 milligrams. What's half of 50 milligrams? 25. How long is it going to take to get from 50 milligrams to 25 milligrams? 2 hours. So that's going to put us 4 hours later. So the bottom line is, it's just that time frame. In this case, the magic thing is the 2 hour time frame. Anytime we shift by 2 hours, we're going to take whatever we had before and cut it in half. What's half of 25? 1250. So 2 hours past the 4, 6 hours from when I started, I should have half of 25 or 1250. Okay, so it's just that idea of how long does it take to cut it in half. So another example, anybody do caffeine here? Okay, a whole bunch of caffeine. So caffeine has a half-life. Can I spell caffeine? I don't know. Is that close? Have 2 F's? Didn't look right, but we'll go with it. All right. So caffeine, half-life for caffeine is about 6 hours. What's that?
Flip the I and the E first.
Flip the I and the E. Thank you. E over here. There we go. Okay. So a standard cup of coffee, like you go make a cup of Folgers coffee, it's going to have about 100 milligrams in it per cup. And that's an 8-ounce cup. So if you have like a double shot espresso, you're looking at like 200-300 milligrams of caffeine in that. So if I look at time in hours versus the amount of caffeine, anybody have a double shot recently? How many you got there? 2 shots, okay. So you're probably starting off with, let's call it 200 milligrams for ease. Probably more, a little bit more than that. Do you guys know lighter roasts have more caffeine? When you roast them, it kind of kills the caffeine, breaks it down. All right. So when am I going to have 100 milligrams? Yeah, 6 hours later. When am I going to have 50 milligrams? 12 hours total, but another 6 hours, right? Yeah, so the bottom line is every time 6 hours goes by, you have half of what you started with, okay? So let's say Emily's still reeling from the play all weekend, and she had like 4 shots of espresso this weekend. That's going to put her up around 400 or 500 milligrams of caffeine. If she's at 500 milligrams of caffeine, 6 hours later, how much is she going to have? 250, whatever half of that is, right? And that's the bottom line, is whatever half of it is, right? So that's the important idea. Changing it into a formula is a little bit trickier. We'll play with more of that later. All right, so now we're going to switch over to carbon 14, and you're going to look at that in 2 different ways. And you can hang out in here and work on this, or you can go to the lab and work on it. First, you're going to use the formula they give and just plug in the years they give you here and figure out how much carbon 14 is remaining. Now keep in mind, what is T measured in here? Okay, and what kind of numbers are they giving us here? Thousands, right? So if they say it's 2,000 years, what am I going to plug in for T in my formula here? 2. Yeah, so just be conscious of what the variable means and how you plug it in. So instead of plugging in 8,000, I'm going to plug in an 8 because T is already waiting for me to use thousands. Okay. I talked about what half-life meant, so you're going to talk about it with respect to carbon 14. Carbon 14 half-life is believed to be about 5,730 years. Okay. So somewhere between the 4,000 years and the 6,000 years is where 50% of what we started with should end up. Okay. So start filling out this table, answering question 2, and then the next table, either on paper or on a spreadsheet. Eventually, I want both on paper and a spreadsheet. How's it going, Elena?
Yeah, I don't have the paper.
Oh, I didn't hand this out?
Yeah.
Shit. I need this. All right. Thank you. No. Oops. Yeah. So you can only start looking at it when something's died, a tree or a person. 2,000 years later, 4,000 years later. So I have some numbers up here if you want to double check to see if yours are coming out okay. No. So 2000 is the number of years, that's what T is. T is measured in thousands. So 2,000 years have gone by, then we say T is 2. So T would just be 2. So notice I have 2 columns in here. Oops. This column got messed up. Center that. If 2,000 years have gone by, T is 2, because T represents how many thousands there are. If 4,000 years went by, T would be 4. So 4 is what I plug into the formula. So we're not solving something, we're just plugging in. So over here, I just asked my computer, what is that 0.8861 raised to whatever power T is? Okay, so this one right here, if I typed it into a regular calculator, it would be 0.8861 raised to the power 4. And that's where I got the 0.616-ish. We'll get to the harder stuff later. This one, we're just plugging numbers into the calculator. Jen, you have the older version of this worksheet. Have it out. Core 4. It's a slight difference in the way I displayed the table in the new version. I think I want to make a note.
So this one's just 0.661. It's just,
yeah, square. Next page. Yeah, so I'm just in this table right here, these numbers, the point I'm making over there is that they just jump each time by another 5,700.
okay.
So just like with caffeine, you went every 6 years.
Yeah.
In this table, we're going every 5,730 years.
Okay.
So just note, that'll make it easier to answer. What's that? So you got, for which one? 175? That's right. That's good. See, I got 0.78, so maybe you typed something wrong. Let's see. The base here. 861.
Oh,
I have
I have 866.
Okay, yeah, that's the base. Do you get the right idea? Spreadsheet's going okay? You can try and answer the next question.
Yeah.
And we're at 14%.
What is the what's the thing
So just like the first, this is the fraction of carbon 14. So initially 0, you have 100%. So if I have 1, which is 100%, how much am I going to have 5,730 years later? Half of that. because that's the half-life.
Okay, that's-
Yeah, so we just keep cutting this in half.
Yes.
That make more sense now?
Yeah.
Okay. Yeah, half-life is deceptively easy. First, it seems a little tricky. How's it going, Emily? Yeah, just keep calculating just like that. Just change the power each time. Lena, how's it going?
All right.
Yeah. Yeah, so starting off with 100%, the half-life is 5,730. You'll have half of what you started with.
And so you
5,200. You just cut the number. You just cut the number above.
this one.
Yeah. Cut it in half.
How many decimal places should we learn to keep?
3 is a good rule on this one.
And just keep it.
It just keeps getting cut in half because you're jumping by 5,730 each time. Yep. That's it.
Yeah. For number 3, did you get 25 for?
Let's see, I didn't do that one yet. So give me just a minute and, I better go over it now since, all right, so we're out of time for fun with math. There was a question on what I got for number 4, is that what you said? 3. Which part of 3?
Just the last number 4.
Oh, the last row?
Yeah.
Is it like 0.06 something maybe?
So I got-
Where's my spreadsheet? Yeah, half of 12 is like 6, so around 6%, 0.0625. Yep. Yep. All right, we will pick this up tomorrow. Be sure to finish up your 4-3 homework, finish your 4-3 worksheet, and start on the 4-4 prep if you haven't already.